In this lesson, we're going to talk about hypothesis testing, which is essentially putting everything we learned in the previous lesson together. So there are two ways we can do a hypothesis test. So the two ways we're going to talk about are the p-value method and the traditional or critical value method. So in order to conduct a hypothesis test on one proportion, we need the formula we talked about in the previous lesson for our test statistic. So again, p hat is our sample proportion, p is the population or the assumed population proportion, and of course q is 1 minus p, and will be the sample size. So we'll need the test statistic no matter if we're talking about the p-value method or the critical value method. A p-value is just the area or the probability of getting something more extreme than your test statistic. So if I calculated a z-score to be about here, the p-value would be the area to the right. And we'll talk about if it's a two-tailed test, then it would also include the area to the left of the negative version of that z-score. So in other words, double this area. So we'll first look at some examples using the p-value method. Among 726 babies born to couples using the X-sort method, 402 were girls. Use these results with a 0.05 significance level to test the claim that the proportion of girls born to couples using this X-sort method is greater than 50%. So let's start out identifying the claim and write it in terms of mathematical symbols. So the claim in this case is that the proportion of girls born to couples using this method is greater than 50%. So we'll use p is greater than 0.5 for our claim. Step 2 then is to identify the opposite. So if our claim was greater than, the opposite of that is less than or equal to. So we would say p is less than or equal to 0.5. Now the third thing to do is identify the null hypothesis and the alternative hypothesis, and then decide which one corresponds to the claim and which one corresponds to the opposite. So remember, the null hypothesis is always the one that has an equals in it. And in terms of our claim or our opposite, the opposite is the one that has the equal sign in it. So we'd say the null hypothesis goes along with the opposite, and our null hypothesis will be that the proportion equals 0.5, which means our alternative hypothesis is the one that doesn't have the equals in it, and that'll be p is greater than 0.5. Now this tells me we're going to be doing a right-tailed test because our alternative hypothesis is greater than. So we'll come back to this in a bit and decide why we had to, or figure out why we had to decide on this correspondence once we get to the end of our hypothesis test. So step 4, we want to calculate the test statistic for this sample, and you can see I've already got it here, but how did we get that? We used our test statistic formula, plugging in what we know. So in this case, p hat, or my sample proportion, was the 402 babies that were girls out of 726 babies born. So 402 out of 726. P is what the population proportion would be if this X-sort method didn't work. So what I'm assuming the population proportion to be is 0.5. You also get that from the null hypothesis, 0.5. So again, q is 1 minus 0.5, and n in this case is 726. So plugging all this into my formula and throw it into the calculator gets me a 2.89 test statistic. So step 5 is to calculate the p-value for that test statistic. That is, we want the probability of finding a test statistic more extreme than ours. So since this is a right-tailed test, the p-value will be the area to the right of our test statistic, 2.89. But if this was a left-tailed test instead, we would find the area to the left of our test statistic. And if it's a two-tailed test, well then it's twice the area to the right if it's a positive test statistic, or twice the area to the left if it's a negative test statistic. So in this case, the p-value is 0.0019. So how did we get that? We had to look up 2.89 in our z-score table. That is our normal probability table. So 2.89 got me 0.9981. So 1 minus 0.9981, since I want the area to the right, gives me 0.0019. Step 6, we decide whether we reject or fail to reject the null hypothesis. To do this, we compare our p-value to our significance level, which was 0.05, and since our p-value is smaller than the significance level, we reject the null hypothesis. If our p-value was larger than the significance level, say it was 0.06, then we would fail to reject the null hypothesis. So the last thing to do is to draw your conclusions or interpret the results in terms of what the original claim was. So let's look back at the beginning to figure out how to do this, and remember that we are rejecting the null hypothesis. So this is what we did at the beginning, but notice in this example we've rejected the null hypothesis. So let me draw a line through there. Notice that the null hypothesis corresponded to the opposite in this example. So since we're rejecting the null hypothesis, that means effectively we have enough evidence to support our claim that the proportion was greater than 0.5. So again, since the null hypothesis went along with the opposite, and we rejected the null hypothesis, we can effectively support our claim. So there appears to be enough evidence to support the claim that the proportion of girls born to couples using the XORT method is greater than 50%. Let's look at another example. So of 745 randomly selected adults, 589 said that it is morally wrong to not report all income tax on your tax returns. We're going to use a 0.01 significance level to test the claim that 75% of adults say that it is morally wrong to not report all income. So first of all, let's identify the claim. In this case, the claim is that 75% of adults say it's morally wrong, which is to say the proportion of adults is exactly equal to 75% is the claim. So we're going to use p equals 0.75 for our claim. The opposite of equals then is not equals. So the third thing to do is identify the null and alternative hypothesis and decide which one corresponds to the claim and which one corresponds to the opposite. So because the claim in this case has the equal sign, that's going to correspond to our null hypothesis. So our null hypothesis will be that p equals 0.75, and our alternative hypothesis will be p does not equal 0.75. Now because the alternative hypothesis is not equals, that tells us this is a two-tailed test. Step 4 then is to calculate the test statistic for this sample. So I'm going to throw everything into my test statistic formula. P hat I'll get from the 589 who said that it is morally wrong out of or divided by 745 randomly selected adults. P in this case is 0.75, which makes Q 0.25, and N of course is 745. So throw all this into the formula and we get approximately 2.56. So the fifth thing to do, step 5, is to calculate the p-value of our test statistic. That is the area or the probability of getting something more extreme than 2.56. Since this is a two-tailed test, our p-value will be twice the area to the right of our positive test statistic. But if this was a negative test statistic, it would be twice the area to the left of a negative test statistic. So let's go to our z-score or our normal distribution table and look up 2.56. 2.56 tells me there's 0.9948 to the left of my test statistic, so I'll do 1 minus that to get the area to the right, which is 0.0052, and of course I'm multiplying by 2 since this is a two-tailed test. So the p-value in this case will be 0.0104. Now we decide if we reject or fail to reject the null hypothesis. But look at the p-value and compare it to our significance level. Our p-value is just a little bit bigger than our significance level. So we're going to fail to reject the null hypothesis. So the last thing to do is interpret the results, and to do that we'll go back to the beginning and figure out which one the null hypothesis corresponded to. So in this case, the null hypothesis corresponded to the original claim. So I'm going to cross out the other one because we failed to reject the null hypothesis. Since we failed to reject the null hypothesis, I'll cross out the alternative hypothesis. But that means, in this case, we are essentially supporting the claim, since we are crossing out the opposite. So there does appear to be enough evidence to support the claim that 75% of adults say that it is morally wrong to not report all income. Now let's look at the critical value method, or the traditional method. So in this example, players make 839 challenges in the first US Open, and 257 of those challenges were successful. Use a 0.01 significance level to test the claim that the proportion of challenges that are successful is less than 1/3. So the claim in this case is that P is less than 1/3. The proportion of successful challenges is less than 1/3. So I'll use P less than 0.33. 1/3, if you plug that into your calculator, you would get 0.33333. Step 2, we're going to identify the opposite as greater than or equal to. So the opposite of less than is greater than or equal to. Step 3 then is to identify the null hypothesis and the alternative hypothesis and decide which one corresponds to the claim and which corresponds to the opposite. Now in this case, since the opposite has the equal sign, that will correspond to our null hypothesis. And since the claim has less than and no equal sign, then that'll correspond to our alternative hypothesis. So our alternative hypothesis is P is less than 0.33, which tells me it's a left tail test because of the less than. And my null hypothesis is P equals 0.33. So now let's calculate the test statistic. Plugging all this into our formula, P hat will come from the 257 divided by 839 challenges. P will be the 0.33 from the null hypothesis, which makes Q 0.67, and N in this case is 839. So plugging all this in, we get a test statistic of negative 1.46. So now let's identify the critical value corresponding to a 0.01. So this is the first place where the critical value method differs from the p-value method. Up until now, they've been exactly the same in the steps. So we want to look at our significance level 0.01 and identify the critical value corresponding to 0.01. That is the critical value, or the z-score, that has 0.01 to the left of it. Now since this is a left tail test, we're looking for 0.01 to the left. But if this was a right tail test, we'd want to know the z-score that had 0.01 to the right of it. And if this was a two-tail test, we would take that significance level, split it into two tails equally, so 0.005 and 0.005, and then decide what the critical values are that separate those areas. So in this case, let me look up 0.01 on my normal distribution chart, which is approximately negative 2.33. So we're going to use negative 2.33 as our critical value. Notice that our critical value, negative 2.33, was further to the left than our test statistic, negative 1.46. So if our test statistic falls into the critical region, which would be the area beyond our critical value, then we would reject the null hypothesis. But since our critical value is further to the left than our test statistic does not fall into the critical region. So we say our test statistic, negative 1.46, is not more extreme than our critical value, so it doesn't fall into the critical region, so we fail to reject the null hypothesis. Now, if our test statistic was further to the left than our critical value, we would reject the null hypothesis. So step 7 now is to interpret the results. Since we failed to reject the null hypothesis, we're going to we're failing to reject the null hypothesis. I'm going to cross out the alternative hypothesis, which means I'm going to circle my opposite in this case. So effectively what I've done is crossed out the claim, which is going to tell me that we don't have enough evidence to support the claim that successful challenges are less than 1/3 of the time. Let's look at this example. In a study of 420,095 cell phone users, 135 subjects developed cancer of the brain or nervous system. Suppose there is a 0.034% cancer rate of non-cell phone users. Test the claim that the cancer rate of cell phone users is different from that of non-cell phone users. We'll use a 0.005 significance level. So the claim in this case is that the cancer rate of cell phone users is different from that of non-cell phone users. So my claim is that P does not equal the 0.034%, but I'm going to change the percent into a decimal. So move the decimal place to the left 2 places, and we have P does not equal 0.00034. The opposite of not equals is equals. So now let's identify the null and alternative hypothesis and decide which one corresponds to the claim and which corresponds to the opposite. Well, in this case, the opposite has the equal sign. So our null hypothesis will correspond to the opposite, and the alternative hypothesis will correspond to the original claim. Now, since the alternative hypothesis is not equals, that tells me it's a two-tail test. So let's calculate the test statistic for this sample. P hat in this case will come from my sample, 135 subjects that developed the cancer out of 420,095 cell phone users. P in this case, of course, comes from the null hypothesis, 0.00034, and Q then is 0.99966. N, of course, is 420,095. So plugging all this in, I get a test statistic of negative 0.66. So I'm going to take my significance level and split it into the two tails because this is a two-tail test and I want to use the critical value method. So I need to find the critical values that have 0.0025 to the right and 0.0025 to the left. So let me look up 0.0025 in my normal distribution. 0.0025 is here, and I see that the z-score that corresponds to that is negative 2.81. So I got negative 2.81, but of course, since this is a critical value, I have the plus and the minus version. So our test statistic, negative 0.66, is not in the critical region because it doesn't fall farther to the left than negative 2.81. So let me say that again. Because this is a negative test statistic, I want to compare it to my negative critical value. If it's further to the left than my negative critical value, then it's in the critical region. Suppose my test statistic was positive, then I'd compare it to the positive critical value, and I would look for if my test statistic is in the critical region to the right. that is further to the right than my critical value. So since our test statistic was not in the critical region, we're going to fail to reject the null hypothesis. So now let's interpret that. Looking back at the beginning, I failed to reject the null hypothesis, so let me cross out the alternative hypothesis, which corresponds to the claim. So since I've crossed out the claim, I can say effectively that there's not enough evidence to support the claim that the cancer rate of cell phone users is different from that of non-cell phone users. So if we took this interpretation further, basically what we're looking at is, according to our sample, doesn't seem to be a higher instance of cancer rates for cell phone users. So you can safely use your cell phone without the risk of brain cancer.